Welcome back to The Explainer. We're actually going to skip the usual preamble today, because we need a high-stakes engineering reality check. Right now, we're talking about what happens when your AI leaves the cozy safety of the lab and hits the absolute chaos of real-world production. Let's get into it. Okay, picture this. Your AI agent just updated a downstream system. Maybe it triggered a financial transaction or a critical healthcare record update. But the network connection died right before the confirmation arrived. So, is it safe to retry? It sounds like a simple question, right? But if you guess wrong in production, the consequences can be literally catastrophic.
Which brings us to Section 1, Demo versus Real-World Conditions.
Look, we all love a good demo, right? The APIs respond in milliseconds, the Wi-Fi never drops, it's perfect. But let's walk through an incredibly common and honestly terrifying real-world scenario. Step 1, a customer requests an action. Step 2, the AI understands the intent and calls the tool. Step 3, the downstream system starts the action. But then, Step 4 happens. The user's connection just disappears. Poof, gone. So what now? Did the action fail? Did it succeed? Did it only partially succeed?
Here is the harsh engineering reality. IP traffic is inherently unreliable. If you look at operating conditions in places like Zimbabwe, or really anywhere across Africa, it serves as the ultimate engineering crucible. Weak connectivity, WhatsApp-first workflows, delayed messages, cranky legacy business systems, these aren't edge cases. They ruthlessly expose every single hidden architectural assumption you made when you were just testing on your local machine.
Let's move to Section 2, the danger of the unknown state.
When that connection drops mid-action, your system enters this dangerous twilight zone. And I really want to emphasize this critical redefinition. Unknown does not equal failed. Think about it. If an AI initiates a payment, the provider completes it, but the acknowledgement gets lost to a timeout, your system is now in an unknown state. If your application blindly assumes that a timeout means it failed, oh man, you are setting yourself up for disaster.
Check out the difference here between a naive workflow and a truly resilient one. In the naive setup, an action causes a timeout, the system blindly retries, and boom, you've just double-charged a customer. Not good. The safer workflow handles that timeout entirely differently. It stops, it verifies the state, it reconciles with the database, and only then does it even think about retrying.
If you're building distributed AI systems, you absolutely have to bake this exact logic into your architecture. It's not optional. Every request needs a unique ID. When a response is lost and the state is unknown, your AI cannot just guess. It has to query the downstream system, verify the actual real-world state, reconcile any differences, and retry only if it mathematically proves that it's safe to do so.
All right, Section 3, idempotency and duplicate submissions.
Imagine a frustrated user on a terrible connection. They're furiously tapping the submit button on your AI chat interface 5 times because, well, nothing's happening on their screen. The crucial takeaway here is this. Message count does not equal business action count. Just because 3 identical requests suddenly hit your back end does not mean 3 business actions should actually occur.
The engineering elixir for this massive headache is called idempotency. It's essentially the mechanism that guarantees an operation achieves the exact same result, no matter how many times it's executed or duplicated. By using explicit deduping and those unique request IDs we just talked about, you force your non-deterministic AI applications to behave predictably, even when the inputs coming at them are totally chaotic.
Moving on to Section 4, surviving partial writes. So what happens when an AI is executing a complex, multi-step agentic workflow? Let's say Step 1 completes, Step 2 completes, Step 3 begins, and then crash. The whole thing goes down. Restarting from scratch might duplicate those steps that already succeeded. But as we can clearly see mapped out here, modern frameworks like LangGraph solve this with deterministic state routing and checkpoint recovery. If a failure happens, the agent can recover from the very last successful checkpoint and loop back safely without doing the same work twice.
Seriously, if you want to move your AI out of the prototype phase, these right here are your absolute non-negotiables. You must have unique request IDs, durable state checkpoints, and dead letter queues. You need transaction reconciliation, strictly safe retries, and, this is a big one, clear human recovery paths for when the automation inevitably gets stuck, because it will get stuck. Section 5. Handling stale AI context. What happens when your AI agent is suddenly cut off from fresh information? Well, it must never, ever simply guess. Depending on the consequences, you need a strict hierarchy of fallbacks. The system might just wait for a reconnection, ask the user for clarity, drop back to a safe static fallback, defer execution entirely, or escalate to a human operator. In these moments, safety always overrides speed.
And finally, Section 6, Testing for the Real World.
Okay, so how do we actually prove that our systems can handle all this chaos? Well, you can't just test the happy path. You have to test the workflow by deliberately dropping connectivity mid-action, delay the network acknowledgements, send duplicate concurrent requests, force uncertain partial states, and just straight up make downstream APIs unavailable. You have to simulate the brutal, unforgiving reality of actual production environments.
And when you run these chaos experiments, sit down with your engineering team and run a rapid-fire postmortem. The first question you ask, what actually happened during the failure? Like, did your logs even catch it?
Second question, could the system determine the real state, or did the AI just blindly assume that a timeout meant failure and start making rogue decisions based on a complete illusion?
Third, could it recover safely without duplicating execution? Did your durable state checkpoints actually work, or did the system just start over and run a critical business action twice?
And finally, could a human operator understand what happened? Look, AI neural networks can be incredibly opaque. Diagnosing a failure is sometimes like trying to find a typo in a dictionary, where every single word is written in invisible ink. If a human can't trace the data provenance and understand the AI's reasoning during a failure, your system simply isn't ready for production.
I really want you to take this away today. An AI that only works when the Wi-Fi is perfect and the APIs are lightning fast, that's just a prototype. A demo proves feasibility, but production proves the engineering.
So, I'll leave you with this question to ask your teams tomorrow morning. Are you testing your AI under the conditions your users actually live in, or are you just testing the illusion? Thanks for joining me on this explainer. Go audit those architectures, and we'll catch you on the next one.